Hey everybody, we're going to try to start a new unit tonight, and that unit is Aromaticity. And in case you're wondering, is it named this way because they smell? That's exactly right. This entire family of compounds was named because a lot of them smell in a very similar way. Aromaticity, at its core, is about conjugated pi bonds in a ring. That's one of the key things we have to have about aromaticity is it has to be in a ring form. Now, does that mean that you cannot have any crap hanging off of it? Absolutely not. You most certainly may. But the core of the molecule has to exist in conjugated pi bonds in a ring. So let's take a look. We're going to go back to this molecule because we just talked about them, the alpha-beta unsaturated carbonyls. And one of the things that we did was we kind of went with this resonance form. Wow, pen is not cooperating today. Hopefully this is familiar to you. Now, this doesn't have to exist in systems this small. You absolutely could have something like this. And in that case, you could have resonance or conjugative delocalization all up and down these pi bonds. Now here's what makes aromaticity different from either of those. In aromaticity, you've got this. In fact, this is important, so I'm going to draw it bigger on the next page. This is benzene. All right? Now, you're wondering, what can I do with this? Well, one of the things you can do is you can push all these pi bonds around. So now, it looks like this. And it didn't shrink in the dryer or anything. This is just how I drew it out. And this can go back and forth. It's because these electrons are swimming around in a completely conjugated ring, a completely conjugated area above and below the plane of this ring. Realize every carbon is sp2, sp2 shape is trigonoplanar, etc., etc. So now you've got all of that, and you could just as easily do this again, and you're back to where you started from. This is why the averaged structure of benzene looks like this. And you are welcome to draw it this way when we don't care about where the pi bonds are. Now, honestly, here that is one step up from phi. There are going to be some times in the future where we're going to start talking about and start needing to use these conjugated pi bonds for reactivity. All right? Now, just a little bit of history here. So people were trying to figure out the structure of benzene for a long time. They knew that it was C6H6, and that's about as far as they got. So some of the proposed structures looked like this. Looked like this, and this is a little hard to draw because I'm doing it in 3 dimensions. This sort of prism-like solid. Where the wedges are coming forward. Another option was this, and this is a bitch to draw, so bear with me. And some even more absurd ones. The one that is commonly accepted is this. The triene form there. Now, this is called the Kekulé form of benzene. Now, there's sort of an urban legend about Kekulé that he had this dream one night while dozing in his chair of Ouroboros. Ouroboros is it's kind of an occultish alchemal symbol, the snake swallowing its own tail. And that's how he came up with the structure of the triene form of benzene. There's been more light shed on it recently, and it turns out he stole the idea from a graduate student. This is not uncommon, or at least it's not as uncommon as it really should be. The other commonly accepted form of benzene, and this guy never gets any love. His name is thiol. The other thing thiol is known for is he developed the way that we take melting points now, putting them in glass tubes, putting the glass tube inside of a furnace. All right, so in addition to just the triene, let's see what it takes to be aromatic. Whoops, sorry. Damn it. There we go. What does it take for a compound to be aromatic, beyond just smelling a certain way? Well, there are several gates that you have to go through. And we're going to talk about these. One is it must be cyclic, like we've already determined. So can you have stuff hanging off of it? Yes. But the core has to be cyclic. Conjugated. Pi bonds. Cations or anions around the ring. It must be planar. Now, this is one that just looking at a structure, especially if you've written it on this or your paper, the planar ring, it's really hard to tell. So you're going to have to just take my word for it when I ask you assume that it is planar if I'm bugging you about it. Finally, it needs to have an odd number of electron pairs. All right? An odd number of electron pairs. So as you're looking at this, how do you count electron pairs? Well, a pi bond is one pair. An anion is one pair. And a lone pair, hold the applause here, one pair. And a cation is 0. So let's look at benzene. Let's put benzene through our tests here. Let's take a look at a definite positive first. All right, benzene. Is it cyclic? Yes. Planar? Just assume that it is. I'll make it really obvious if it's not planar. Okay, whoops. Extreme close-up. Sorry, my screen shifted on me there. All right, is it cyclic? Is it planar? Yes to both. What else can we say about it? All the pi bonds are conjugated. Meaning you can push it all around that ring like we demonstrated recently. Finally, let's count up the number of electrons we have here. 3 pi bonds means 3 electron pairs. This is aromatic. This is the cyclopentadienyl anion. Man, try saying that when you're drunk. What I'd like you to do is figure this out. Is this aromatic or not? I'll give you a minute. All right, you're back. This, ladies and gentlemen, is aromatic. Now let's think about this one. The cyclopentadienyl cation. Do the analysis. I'll be right back. Hey, welcome home. Okay, so this actually has 2 electron pairs. This is its own state at this point. This is what we call anti-aromatic, where these other ones are aromatic. What's so special about aromaticity? Well, it is a massive stabilizing force. And anti-aromaticity is very destabilizing. All right, I'm at 11 minutes, so I'm going to go ahead and call it quits for this one. The next video we do, we're going to look at some more examples of aromaticity, and then after that, we are going to start my favorite unit in the class, which is electrophilic aromatic substitution. The reason I love this one so much is, and I say this not bragging, I was part of the research team that finally put this mechanism to bed in the mid-90s. So it's just a little point of pride for me. All right, everybody, have a great day, and I'll see you soon.